Grade 11s, we're on our second part of the sine law tonight, and we're looking at the ambiguous case, which is a scary sounding title, but we're gonna be fine. I'd like you to consider a triangle ABC, where I know these two things. This side is 50, we won't do units, and this is an angle of 28 degrees. So I'm just going to use SOHCAHTOA for a moment to consider the side BC. So for the SOHCAHTOA in a right angle triangle, I would look at opposite over hypotenuse. So I would set up my ratio. Sine of 28 degrees is BC over 50. BC is 50 sine 28. BC is 23.5. So if BC were exactly equal to 23.5, then triangle ABC is a right angle triangle. Okay. There is one answer to this problem. What is the opposite side of the triangle to angle A? What if in fact I wasn't sure that that angle is a right angle triangle in there? Then I know something. If BC is shorter than 23.5, and I am locked with my length of 50 and my angle of 28 degrees, so I can't change that in my triangle. And if BC were to be shorter than that 23.5, then BC is going to just dangle here. It wouldn't be long enough to meet the other side. So there would be no solution, or no triangle, I guess is maybe a clearer way to say it. There would be no triangle to fit that data. 28 degrees, length of 50, opposite side, wouldn't work to be smaller than 23.5. And in the same token, if I happen to know that BC were larger than 23.5, then BC would hang down here. So there are possible solutions, but I would have to bend back at B to meet the bottom in a different way than I just drew it. So BC is longer than 23.5. Then BC would have to move back here. There. That's longer than 23.5. Or it might go that way. We don't know the length of AC. So we have two possible triangles that would fit the data, 28 degrees, length of 50, and BC, if BC is larger than 23.5. Consider the following triangle. We have triangle KJL. I have that angle J is 52, little side j is 25, and little side L is 28. And I've been asked to solve the triangle. So I have just drawn a triangle. It is not going to be proportional. It's just to get me started. So let's label this KJL. And I'm going to have little j, little l, little k, just to get sort of a rough idea here. I've been told that angle J is 52 degrees and side little l, I'm just jumping to this one, there's a method to my madness, 28. Now I wasn't sure how to draw my triangle, whether it should look like that or look more like a right angle triangle. So just forgive me while I do a little math off to the side. If this side was drawn as a right angle triangle, what would the length of a right angle triangle be if I had 52 degrees and a length of 28. I'm just going to do some math over here. Sine of 52 equals opposite over hypotenuse, which would be that little height over 28. So that little height would be 28 sine 52, which would be approximately 22.1. Okay, so the length that I'm missing, that j, is 25. 25 is longer than 22.1, so it is not, that would be 22.1. It is not a right angle triangle. So that was correct that I drew it not as a right angle triangle, but if j is 25, I might have drawn it that way, or I might have drawn it this way, 25 meters. I don't know if I should have drawn triangle KJL like I did originally as an acute triangle, or perhaps it's an obtuse triangle where my 25 is here, my 28 is here, my 52 is here. Either scenario would work for a length of 25. It is a longer length than 22.1, so it's not a right angle triangle, and it's not too short and dangly like we looked at the last slide. So either one of these solutions would work. And we don't know which is the correct solution because we don't have enough information. So we're going to solve both possibilities. This is called the ambiguous case. When you have a side and an angle, and another side, and the angle that you have is not between them, you don't know which of the two possible solutions there are. The acute triangle or the obtuse triangle solution could both work for the information you're given. Number one, let's solve for the acute triangle. We want to find side K, we want to find angle L, and angle K as well. So I'm going to use, as always, I'm going to use the sine law to solve this thing. Sine of 52 over 25 equals sine of L over 28. I'm going to leave the K's for now because there's two things that we don't know there. So to solve for angle L, I'm going to multiply both sides by 28. Sine of L as a decimal 8826. To find an angle L, I'm trying to make those look different. Angle sine and L is second function sine of that decimal. 61.95, 62 degrees. So that makes sense in the triangle that I have above. My calculator gives me that acute angle L. And from there, I can say, all right then, angle K, following from that acute possibility for L, would be 180 minus 52 minus 62, 66 degrees. And the last side we have would be sine of K, sine of 66, sorry, I have that, over little k equals, you can pick either ratio, but I'm going to go for sine 52 over 25. I'm going to cross multiply or multiply both sides by 25. Multiply both sides by k. Divide both sides by sine 52. I get for k approximately 29. So if my original diagram was correct and I had an acute triangle, the measures are 66 degrees, 62 degrees, 52 degrees, and lengths of 28, 25, and at the bottom here 29. However, If it is actually an obtuse triangle, then let's solve the obtuse possibility. So I have just a really rough sketch again, 28 with 25 kind of coming backwards with an obtuse angle at L. J is 52 degrees, and K. I'm going to set it up as I always have. Sine of 52 degrees over 25 equals sine L over 28. Well, I know what my calculator is going to give me. I've already done the work on that. So the first possibility when you type it in your calculator is going to be 62 degrees. We know from our diagram, however, that it shouldn't be 62 degrees. It's an obtuse angle. So angle L is not going to be 62 degrees in this triangle. It's going to be 180 minus 62 degrees. And we have that from our angles of rotation, that to get a second possibility when you have a sine angle is to do 180 minus the original answer from your calculator. So angle L in this case would be 118 degrees. Well, that changes everything. Angle L is 118 degrees, then angle K, which is 180 minus the 52 that we have, minus 118, is 10 degrees. So we have the three angles now. The only thing we're missing is side K. So we need to solve it like we did here, but the numbers are all different for this particular triangle. I have sine of 10 degrees over little k equals sine 52 over 25. So very much in the same way, I'm going to solve for k. I'm going to multiply both sides by 25, multiply both sides by k, divide by sine 52. And I should get a much shorter, I keep doing that, get a much shorter k. K is approximately 5.5. Okay, as opposed to 29 in the last one. So with the same information, we've come up with two possible accurate answers. That is the ambiguous case. So for the ambiguous case, the only time we need to consider the ambiguous case is when you are given two sides and a non-contained angle. That means not the angle between those two sides. Okay. So if I'm given angle A, little side A, and little side B, I must consider the ambiguous case because I have two sides in a non-contained angle. When I'm given that information, you know you will use the sine law because you are given an angle and opposite side pair. So the ambiguous case only happens when you're using the sine law. Sine law. When you're given two sides in a non-contained angle, then if the ambiguous case needs to be considered, it's when that side A, the one that's across from the angle, is longer than what would be required for a right angle triangle. So if A is equal to B sine A, then you have a right triangle. There is one solution to the problem. It is a right triangle, and we proceed from there. If A is smaller than B sine A, which means it's too short and it's dangly. I don't know if that's a word, and I don't know if you should write it down. It's not very mathy. but it's dangly like we showed you on the last two slides. There is no triangle possible that fits your data. If A, however, is longer than a right angled triangle would allow, like the last one, when we looked at the last one, I compared that 25 to the length of 22.1. It was longer than 22.1, so I had to consider the ambiguous case. If it is longer than what a right angle triangle would give, there are two solutions. One is an acute triangle. One comes from an obtuse triangle. This is called the ambiguous case. We're going to solve for R. It's an ambiguous case question, so it's going to take me about 3 minutes. Here we go. I have an angle, 30 degrees. I have two sides, and this angle 30 is not contained between them, so I must at least consider the ambiguous case. I'm going to compare the 5.3 to 10.6 times tan sine 30. So is 5.3 equal to 10.6 sine 30? If so, then it's a right angled triangle. If it's larger, so if it's equal, you'd have a right angled triangle. If 5.3 is larger than 10.6 sine 30, then I have two possible solutions. It's the ambiguous case. If 5.3 is actually smaller than 10.6 sine 30, we have no solution to this triangle. It's like it's dangly. Okay? So we need to compare. Let's type in into our calculator 10.6 times sine of 30 degrees, which is a special angle. I should have been able to do that in my head. 5.3. 5.3 is exactly equal to 5.3. So we have a right angle triangle. I should have drawn this as I can solve this triangle using SOHCAHTOA. I do not need to consider the ambiguous case. For the next one, I have a triangle where I have an angle and two sides, and that angle is not between the two sides, so I need to consider the ambiguous case. I am going to compare 6.7 to 12.4 times sine 26. So from the slide where we were looking at the ambiguous case, I'm comparing little side m to n sine m. If it is exactly equal, I have a right angle triangle, one solution. If it's smaller, no solution. If it's larger, two solutions. So I'm going to type the right side. 12.4 times sine 26 is 5.43. 6.7 is larger than 5.43. So I do have the ambiguous case. I have to consider that there are two solutions to this problem. And we need to find both of them if you're asked to solve for p. There are two possible values for p. So solution number one. I am going to solve an acute triangle. I'm going to take my calculator's value, face value, and solve. Here we are, sine 26 over 6.7 equals sine n over 12.4 sine p over little p. And it's little p that I want to find eventually. For this particular problem, n is going to be an acute angle. When we do the second solution, I will think about the other n, which is the obtuse angle. All right, calculator, here we go. I want to solve this ratio right here. I'm going to multiply both sides by 12.4. 12.4 sine 26 over 6.7 is sine n. I will get a decimal for that. 0.8113. If I second function sine that answer, 54.2 degrees. Oops, that's n, not sine n. Okay, I have an acute answer for n. So my P, angle P, will be whatever's remaining. 180, subtract the 26, subtract 54.2, and I have my angle P. P is 99.8 degrees, and if I want to solve for little p, I have my sine ratio above. I'm going to use sine of 26 degrees over 6.7 is sine of 99.8 over little p. To solve for little p, I've got to multiply both sides by p and 6.7. And then I'm going to divide both sides by sine 26. And my calculator will give me, there we are, approximation all the way down. Here we are. P is about 15.1 in length. There is a second possibility. Since I have the ambiguous case, there might be another answer equally valid. So the second answer is where I look at n and say my calculator only gave me the acute possibility. I need to consider the fact that angle n might be an obtuse angle instead. So I'm going to give my second answer with obtuse n, 54.2. In this case, n is 125.8. My m is 26, and so my p also will be different. It won't be 99.8 anymore. 180, take away 26. Take away 125.8 degrees. So in this case, I can't do two things at once. Minus 125.8, I am left with 28.2 degrees. So for the second solution, to find little p, I set it up a little differently. It's sine 26 over 6.7, but it will be equal to sine 28.2 over p. Little p, same process. Multiply both sides by 6.7 and multiply both sides by p. Divide both sides by sine 26. So lots of repetition. In this particular case then, p is 6.7 times 7.2. So the two possible solutions for p are 15.1 or 7.2. One last question considering the ambiguous case. The light from a rotating offshore beacon can illuminate effectively up to a distance of 250 meters. So I am looking from the sky down, and I have this beacon. From this point, the sight line to the beacon makes an angle of 20 degrees with the shoreline, and the point on the shore is 500 meters from the beacon. So we've got the beacon here, we've got this little point on the shore right there, and the light from the beacon can light up to 250 meters. So this guy can shine 250 meters I just don't know if my diagram is right. So I have an idea of what's going on, but let's just check. Since I know an angle, a side, and an opposite side, I might have the ambiguous case. So I'm going to compare 250 to 500 sine 20 degrees. If it's exactly equal, I have a right angle triangle, and so on. So 500 sine 20 is 171. 250 is way bigger than 171, so definitely like that. That means I have the ambiguous case. That means that point at B could extend that way or that way, and I see a distance along the shoreline that the question is asking me to look for. So I want to find the distance along the shore that it can light from here all the way along the beach to here. We know for the ambiguous case we have two solutions. The first solution is where we have triangle ABC, where ABC is an acute triangle. Or at least the angle at C is acute. That's what our calculator is going to give us by default. So I want to find, on that triangle, I want to find length AC. I can find that length along there. That will help me to find the length along the shoreline that the light is shining. Solution 1, set up the sine law. Sine of 20 degrees over 250 is equal to sine B over little b equals sine C over 500. It's the C that I'm going to get my answer for, and it's going to give me an acute answer in this first solution. Sine 20, so I'm really working at these two ratios together. Sine 20 over 250 equals sine C over 500. Multiply both sides by 500 to get sine C by itself. Sine C is a decimal, 0.684, which gives me an angle for C, and I second function sine that answer, 43 degrees. If C is 43 degrees, then I have angle B as 180 minus the 20 minus the 43. I am left with, for angle B, 117 degrees. I wanted to find side AC, which is little b. So I'm going to just finish this part up by finding little b. So sine of 20 over 250 equals sine 117 over little b. So little b is cross multiply. B would be 250 sine 117 over sine of 20. Should be a big number. Approximately 651. So on my diagram, this whole length AC is 651 meters. I am going to do the other possibility, and I'm going to put a little d here. My obtuse solution, which is the second solution, I am looking to solve triangle ABD. I don't have to start writing with my ratio. I just know that at this point, my numbers are going to be different. So my second solution can kind of start halfway down. Angle C in the second possibility, triangle ABD, which is not a C anymore, it's a D, isn't it? I changed the letter. It's an obtuse angle, and I can get that merely from 180 minus the 43. 137 degrees. In that particular case, I have an angle at B which is now altered. I am locked with the 20 degrees. My D is 137. The B in that triangle is 180 minus 20 minus 137, 23 degrees left for B. So this changes as well in the second solution. And then we are going to solve for AD. So sine of 20 degrees over 250 is equal to sine D over D, which will be, sine B over B, sine 23 degrees over little b in this case is the same as AD. So I can find side AD. I'm cross multiplying or multiplying both sides by AD and by 250. Side AD is 250 sine 23 over sine 20. AD is 285.6. 285.6 right there, so that the distance DC, which is what we've been looking for all this time. So DC, the distance illuminated, is the 651 subtract at 285.6, 365.4. All right, ambiguous case is a toughie. I taught it in 32 minutes. I think that's a world record. Here's some pages to work on.